Hi, and welcome to my presentation. I'm Jens, and I will talk about VEDLIoT, which is short for Very Efficient Deep Learning in IoT. VEDLIoT is an EU-funded project which aims at providing a flexible, scalable platform for AI in IoT. We are developing the hardware. In addition, we are looking at different accelerators to boost the energy efficiency by FPGA and ASIC technology, as well as the toolchain mapping these heterogeneous hardware substrate towards the use cases. With respect to the use cases, we are focusing on 3 use cases from industrial IoT, automotive, and smart home. And via an open call in the project, we are getting additional use cases for early use and evaluation of VEDLIoT technology across a broader range of use cases. VEDLIoT consists of 12 partners spread all across Europe, starting from Portugal, across Switzerland, Germany, Poland, and Sweden. This is the VEDLIoT big picture. As you can see here at the bottom, we have the different hardware platforms, starting from the embedded or far edge range all the way up to the cloud. On top of this, we are building the different accelerators and also a modular microserver approach integrating ASIC as well as FPGA technology. To map these hardware substrates then to the hardware, we are introducing a middleware, including an optimizing compiler, an emulation platform, as well as benchmarking and deployment technology. This is then used by the different applications from the areas of smart home, industrial IoT, or automotive AI. As said, all this is then boosted by the open calls providing additional use cases. We also have a requirements engineering part in VEDLIoT, dealing with the different aspects of developing, specifying, and validating edge IoT systems, as well as security and safety aspects, dealing, for example, with things like trusted execution and communication or monitoring of IoT systems. The different aspects of the VEDLIoT project. The VEDLIoT hardware platform provides a heterogeneous, modular, and scalable microserver approach, starting really at the far edge or embedded computing domain all the way via edge to cloud computing. It can integrate various heterogeneous hardware approaches in the system so that it really covers a wide range of possible applications and improves on the one hand performance, maintainability, reliability, as well as energy efficiency and safety. I will now explain the cloud platform in more detail. This is called Rexbox. The Rexbox features a modular approach integrating high performance as well as low power carrier. Using this technology, you can integrate the full spectrum of microserver technology, starting from classical x86 servers across ARM, FPGA, as well as GPU technology. In addition to this, we also have the possibility to integrate PCI Express-based accelerators, such as, for example, Tesla GPUs, all connected via a flexible communication infrastructure, which is shown here at the bottom. In addition to the Rexbox, which is focused more on the cloud, we also have the T-Rex, which is focused at the near edge. The T-Rex edge server platform is optimized for local edge applications, has a similar approach as the Rexbox in terms of modularity, which means that it also uses a heterogeneous microserver approach, but provides more flexibility with respect to I/O, really optimized for quite compact form factors and can also serve embedded applications. The MicroRex platform features far edge applications. It basically has the same modular concept as the T-Rex and the Rexbox platforms. However, it is a scaled down approach using smaller microservers like SMARC, Jetson NX, or Xilinx Kria. It has a wide range of communication interfaces, really targeting small embedded use cases. This is an overview of the different microservers developed within VEDLIoT for the platforms like the Rexbox, the T-Rex, and the MicroRex, which has been introduced before. Apart from the classical CPU-based microservers like COM-Express or COM-HPC, we also have the possibility to include more low-end microservers such as APALIS or SMARC. We also have FPGA or GPU technology in various form factors, as well as specialized machine learning ASICs. All those microservers are developed using industry standard form factors, which we are also influencing and standardizing within VEDLIoT. Examples of those are COM-Express and COM-HPC, defined by the PICNIC consortium, Jetson AGX or Jetson NX, defined by NVIDIA, Xilinx Cria, SMARC, or the Raspberry Pi compute module. In this spider chart, you can see the different capabilities of the module. Some of them are really small and more balanced, for example, the COM-Express or COM-HPC ones. Others are very specialized in terms of architecture. For example, the Jetson ones only supporting GPU architectures, or really focusing on performance, such as COM-HPC. What you can see here are first results from the project. What we did is basically benchmark different accelerators, like GPU-based ones, FPGA-based ones, or classical x86 or CPU-based ones in terms of their performance for a particular network using different data types. Looking at the power consumption as well as the performance. You can see that these axes are scaled in a logarithmic fashion, so that basically you can observe the general trends that also lower power leads to lower performance. But what you can see, for example, here is that especially the GPU-based systems here give a very good power performance ratio, so providing a very good energy efficiency. As said, we have done this for different benchmark data sets, for example, YOLO V4, ResNet 50, which does not shows that much different compared to YOLO, or MobileNet, which, as you can see here, overall provides a little bit less performance compared to YOLO or ResNet. When you then compare the energy efficiency, you see that especially the GPU-based platforms, for example, the AGX, the Xavier AGX or the GTX-based ones are showing a quite high energy efficiency. We are going up to 350 gigaops per watt here using the ResNet 50 dataset with an int8 data types. This is, let's say, just started, so this is work in progress. We are also continuing this work, including more specialized accelerators. This is a comparison chart of accelerators that we are currently looking at. Some of those already evaluated, like I said, all the GPU-based or most of the GPU-based architectures. However, you also see that we have a couple of more specialized accelerators in here, such as the coherent logic ones in here, or let's say low power architectures like the NDP 120. In general, you see that all those show an average efficiency of up to 1000 gigaops per watt or 1 teraops per watt based on vendor values. So that is something that we will look into in the future and will get additional results. With respect to the accelerators, we are not just using the heterogeneous accelerators and then compile the applications according to those accelerators. But as we are using FPGA technology in the project, we can really tune both sides. So we are featuring a co-design approach here, optimizing the accelerator on the one hand, and the use case or the toolchain on the other hand, so that we can really get the best efficiency here, which is possible for a particular use case. The toolchain, as said, on the one hand, combines on an optimizing engine, integrating the results of the what we call VEDLIoT model zoo. So results from things like image classification, object detection, and so on. Available compilers and runtime APIs, which then map those to the heterogeneous hardware substrates, so the Rexbox, T-Rex, or Microrex that I presented before during this presentation. In terms of use cases, we have 3 use cases in the project. First one is the smart home or assisted living use case. The general idea here is to increase safety, health, and well-being of the residents in this home. We are looking at a smart mirror as the central user interface. This smart mirror is then controlled via gestures and voice, showing also personal information, and is considered as really the central control point for the whole smart home. Data privacy is seen as the highest priority here, so all the computations and all the data is processed local and not sent to the cloud, as it's the case for existing solutions. The smart mirror is combining face recognition, object detection, gesture recognition, as well as speech recognition. So it's really a full-featured AIoT application, which provides different optimization and different possibilities for improvement using the modular microserver technology that I just presented. An additional use case is the industrial IoT use case, in particular the drive condition classification. The idea here is to develop a small device running on battery for several years. So you have quite an energy constrained application here. Nevertheless, it should include several sensors such as acceleration or accelerometer, magnetic field, and temperature, thereby providing the capability to then really do AI or deep learning on a very in a very energy constrained environment, with the ultimate goal of predictive maintenance. So basically monitoring the electric motor or the electric drive, providing information when this motor is going to need maintenance, when it's going to fail, so that you can detect cooling faults, bearing faults, and so on. An additional use case from the area of industrial IoT is the arc detection use case. The arc detection use case targets electrical cabinets where electrical arcs can occur due to switching activities. The main challenge here is, on the one hand, the response time. You want to detect an arc and act quickly when you have detected an arc. On the other hand, the detection accuracy for both false positives as well as false negatives, because switching off such a cabinet, if you do a wrong detection, is very expensive, as you potentially switch off machinery and damage existing processing. On the other hand, not switching off in case there is really an arc can be even catastrophic, because it then basically fails its purpose and can even cause physical injury to involved people here. The third use case is the automotive use case. The automotive use case deals with the challenge of pedestrian detection for different scenarios, like, for example, urban areas, so within a city as well as on the countryside. All this processing should then not be done within a single ECU, but should be really spread across the car, across the edge, all the way up to the cloud, so that you can really use the full range of VEDLIoT technology and also reconfigure your application so that you can then adapt to those different scenarios in an efficient and smart way, not wasting any computational resources, providing the optimal configuration for the different for the current scenario. This finishes my presentation regarding VEDLIoT. You can follow our work on social media or the website. You can also apply for the VEDLIoT open call, which is open now, which allows you to be part of VEDLIoT and have early access to VEDLIoT technology for your own IoT use case. So this is something that I really recommend. You can receive additional funding while using the latest VEDLIoT technology. That's all from my side. Thank you for your attention.